This presentation is a first introduction to the exciting world of organic chemistry. By the end of the presentation, you should know what we mean by organic chemistry. You should have a sense of carbon's central role in this field and also the number of bonds that carbon can form in a molecule typically. You should know how to represent organic molecules using a few different styles: full structural formula, shortened structural formula, skeletal structural formula, and the molecular formula. So let's start by considering what we mean by organic chemistry. And essentially it's the study of molecules based around chains of carbon atoms like the one you see here. It doesn't have to be many carbon atoms. In fact, some organic molecules only have one carbon atom in, but they're all kind of built around carbon atoms. Note that that is very different from the use of organic in everyday language, where it means food that's been grown naturally without the use of artificial fertilizers or pesticides. Organic molecules in chemistry are not necessarily naturally occurring. Many of them are man-made. So it's this feature of carbon chains that is the essential thing for organic chemistry. One of the key features of organic chemistry is understanding that carbon atoms form four bonds. So whenever you're drawing organic molecules or thinking about organic molecules, you need to be checking that the carbon atoms all have four bonds. If you look at the molecule above, you can see that each carbon has formed four bonds. In this case, it's four single bonds. So there's a few possibilities for carbon. It might form four single bonds around itself. It might form two single bonds and one double bond, so the double bond counting as two bonds, so we still add up to four there together with the two singles. And you can even get a situation where you get one single bond and one triple bond, though that does not play a big part in our study of chemistry at A-level. You might well have had some experience of organic chemistry at school with studies of molecules such as the alkanes, and certainly the molecules on the previous slide might have looked familiar to you. But as we go on through our study of organic chemistry, we'll see that it's not just carbon and hydrogen atoms that take part. There's some other fairly common elements as well, and we'll just introduce a few of those here. So carbon chains form the heart of the molecules. You get many hydrogen atoms, and certainly effectively wherever you need to fill in a bond for carbon, it can be assumed to go to a hydrogen unless told otherwise. But what else can we find? Well, we can also have oxygens. Oxygens form two bonds, so you can have an oxygen double bonded to a carbon. We can also have nitrogen. Nitrogen forms three bonds, and again we'll fill in the gaps with hydrogens. We can get halogens, such as chlorine and bromine, fluorine and iodine as well, taking part in organic molecules. And just another example of oxygen showing that it doesn't have to be a double bond. It can make two single bonds, and then filling in spare bonds with hydrogen again. So hydrogen is certainly the most common thing we find in organic molecules apart from the carbon atoms, but we do get these other elements as well, and this is a list of the kind of thing that you're going to be seeing involved in organic molecules during your A-level study. One thing you'll very quickly realise with organic chemistry is that there's just a vast, bewildering array of these molecules, and it would be an impossible feat to sort of memorise them all. A lot of them have common names: caffeine, aspirin, paracetamol, glucose, all sorts of things like this. But just the name itself really doesn't tell you very much, unless you'd memorised what that molecule actually is. You couldn't really unpack the name to give you any information about the molecule. So chemists need ways of communicating to each other about these molecules so that they can really understand what the molecule is. And you need to know a few different ways of doing that. One of them you've probably come across already at school, and that is the kind of drawing where you show every single atom and every single bond connecting those atoms. And this has a name. This is known as the full structural formula of the molecule. In a way, it's the clearest representation of the molecule, and you can just look at it and fully understand, without any specialist knowledge, exactly how that molecule is structured. But, as I'm sure you found at school, rather time-consuming drawing them out when you get to the longer molecules. We'll use the same molecule to introduce some of the other styles of representing a molecule, and at the other end of the spectrum in terms of complexity is what's known as the molecular formula. The molecular formula simply tells you how many of each different type of atom are present in as simple a form as possible. So a typical molecular formula for an organic molecule will start with C, and it'll then have a subscript after it showing how many C atoms are present, 3 in this case. Then it'll tell you the H's, and how many of those are present, 6 in this case, and then it'll tell you any other elements present, so 1O in this formula. You have to condense it right down to that, so sometimes on the internet or in textbooks you'll see alcohol, such as the molecule here, shown with an OH group at the end of the formula to show you that it's an alcohol. That actually is not a true molecular formula, and you'd lose a mark in the exam if you wrote that. You have to condense it right down, the number of carbons, the number of hydrogens, the number of oxygens, and the number of any other elements present. The next format we'll look at for representing a molecule is probably the favourite one for most chemists because it's a very efficient technique. It's called the skeletal formula, and it's efficient because it leaves out a lot of unnecessary information. For instance, chemists know that these molecules are based around chains of carbon atoms, so why bother drawing the carbon atoms if we know that they're going to be there? Now, that would leave a problem, of course, because if we just drew the bonds, we'd end up with a straight line, and how would you know how many carbon atoms were present? To get around this, what we do is we zigzag the bonds between the carbons in the chain. For the molecule above, you'd get something like this, and you can see that we've got the double bond represented on the left as the first zig or zag, whatever you want to call it, and then we've got the single bond. So for 3 carbon atoms, we're going to get a zig and a zag, so to speak, for the bonds between them. You'll notice that we haven't drawn the hydrogens or the bonds to them at all, and again that's because a chemist knows that unless something else is attached to a carbon, it'll be hydrogens making up the 4 bonds required. So we don't do anything about the hydrogens and the bonds to them, but we do need to show any other atoms or groups of atoms that are attached. And in the molecule at the top here we've got this OH group. So what we do is we just carry on our zigzag to an OH. We don't bother drawing the bond between the O and the H in the skeletal formula. And so we end up with the complete skeletal formula looking like this, and you can see hopefully that's a big time saving over drawing out that full structural formula at the top. In case you're worrying, does it matter whether I start my zigzag going up or down? The answer is no, it doesn't. So we could equally have this molecule represented the other way up, and it doesn't really even matter which end you start drawing at, so we could also show the skeletal formula in these other 2 ways. Another fairly efficient way of representing a molecule that you need to be aware of is called the shortened structural formula. It's something you might see from time to time, and you need to be able to interpret them, but it's unusual for you to actually be asked to represent a molecule this way. So what is a shortened structural formula? Well, it goes along the chain and kind of summarizes what's attached to each carbon. So if we look at this molecule, working from left to right, on the first carbon, what's attached is 2 hydrogens. And so we can write C, and then what's attached to it, following it, H2. That's then connected by a double bond to another carbon, and the only thing attached to that carbon is an H, so we write CH. That's attached to another carbon with 2 hydrogens on, so CH2, and then attached to that at the end of the chain is an OH group. Sometimes you see an even shorter shortened structural formula where you don't even show the bonds, and so we'd get something like this. Of course that misses out that double bond information, but as a chemist you could deduce there's a double bond there, because if there wasn't, then the first and second carbon on the left wouldn't have enough bonds to make up the usual 4 bonds per carbon. For the sake of completion, I'll just mention here that as well as these kind of drawing styles of representing a molecule, there's also something called systematic naming or systematic nomenclature, to use its very technical term. And this is a series of rules that allows you to produce a name in words for a molecule, words and numbers, that a chemist could turn into a structure. So, for example, the molecule above would end up as 3-hydroxypropene using this system. There's endless rules for all sorts of different types of molecule, and we won't go into those here, but as you go through the A-level course, you'll be learning a lot of the rules involved. Well, here's a chance to see how much you've picked up from the video with a few quick questions. In this first question, somebody's tried to draw a molecule using a full structural formula, but they've made some mistakes in terms of the rules you've learnt about carbon in these organic molecules. Pause the video and see if you can spot their errors. So hopefully you spotted that for this carbon circled here, they've drawn too many bonds. There's 5 bonds showing carbon does a maximum of 4 bonds. And so effectively they've filled in an additional hydrogen on that carbon that shouldn't be there. Moving along to the next carbon, same problem again actually. 5 bonds showing maximum of 4 possible. So again, whoever drew the structure has put on a hydrogen that shouldn't be there. When we get to the final carbon though, we've got the opposite problem now. There's only 3 bonds showing, carbon needs 4. And so in this case the person has probably missed off the hydrogen that should have been attached at the end of the chain there. For your next challenge, have a go at converting this full structural formula into a skeletal formula. Pause the video and see what you can sketch. So you should have spotted that there's 5 carbons in the chain. That'll give a zigzag in the shape of an M, or maybe you did it upside down, look like a W. And then you've got the OH group to attach to the middle carbon. The easiest thing is a stick coming straight out from the point at the 3rd carbon with the OH on the end of it. If you drew it the other way up, it would look like this. Here's another opportunity to convert a full structural formula into a skeletal formula. Look carefully, count the number of carbons, draw the zigzag for the chain, add in any other bits and pieces that need to be shown in a skeletal formula. So pause the video and have a go at drawing the skeletal formula. So you should have got this. You've got 5 carbons in the chain, so you're going to draw an M or a W for the carbon chain, and then you've got the NH2 group and the double bond to the O sticking off an end carbon and the double bond and the final bond at the other end. If you did it the other way up, it would look like this. This time have a go at doing it the other way around. Here's a skeletal formula. Pause the video and try and draw the full structural formula for the same molecule. So if we work from left to right, at the end we've got a CH3 group. Next is a CH2. The next carbon along would have just 1 hydrogen attached, and then there is a carbon with 3 hydrogens sticking off the chain. Carrying on along the chain we get to another carbon that's got a double bond O, and of course to make up to 4 bonds for that carbon we need an H. And here's another one to convert to a full structural formula. Pause the video and have a go. So potentially a bit more exciting, this one. We've got a ring of 6 carbons in the form of a hexagon, 6-membered ring. And then if we add in the bits and pieces attached, we've got a double bond between 2 of the carbons. And then we've got this 2-carbon chain sticking off the side. We've got the OH group at the end of that. And remember, for full structural, you need the bond between the O and the H. And then we can fill in the other bits and pieces, bringing the carbons up to 4 bonds, not forgetting that bromine atom. And we should end up working through to look like this. So just check carefully, make sure that you've added the right amount of hydrogens for each of the carbons. A common question in the exams is to convert a skeletal formula into a molecular formula. So see if you can remember what a molecular formula is first, and then have a go, pause the video and convert this skeletal formula into the molecular formula for the molecule. Okay, working through, we can count the number of carbons. We find there's 5 of them highlighted there, so C5. Hydrogens is a bit more of a challenge, and remember what you need to do is go through and just make sure that each carbon has enough hydrogens to give 4 bonds for it. So starting from the left, we'll have 2 hydrogens on the first carbon, just 1 on the next one, 1 on the one after that, then 2, and then none. So that's 6 hydrogens directly attached to carbons, but we've also got the 1 in the OH group and the 2 in the NH2, so H9 for hydrogens. And then we've got the 1N in the NH2 group, and we've got the 2 O's as well. So C5H9NO2. It wouldn't matter if you had put the N and the O's the other way around. And since you had such fun with the last one, here's another skeletal formula to turn into a molecular formula. Pause the video, see what you come up with. Okay, so this time we've got 9 carbons highlighted there. We've got 15 hydrogens, which are all sketched in there. And then we've got the 1 chlorine. So C9H15Cl. Just check that you got the right number of hydrogens squeezed in. Remember, the rule is 4 bonds for every carbon. Have a look at what's there and then add in hydrogens to make it up to 4.